Hi everyone, welcome to this episode of Keipert Labs. In today's episode we're going to talk about the reaction quotient, or Q. We're going to start by looking at when is a system at equilibrium. We're then going to introduce this reaction quotient, or Q, a measure that will help us to decide or address this question. And then we're going to look at the relationship or comparison between Q and K, our equilibrium constant. So when is a system at equilibrium? We've looked in the past about what it means for a system to be at equilibrium, because then remembering that they have certain qualitative characteristics, looking at this idea that there's no macroscopic changes, the rates of forward and reverse reactions are equal and non-zero, and so for it to be a dynamic equilibrium. But this idea that there's no change in concentration once we've established that point. Now we can graph it, we can look at it over time, and we can actually, we can monitor these things, and we can look at when the graph is horizontal, when there's no net change in concentrations to help us to decide. But quantitatively, and without kind of going to this extent of monitoring things over time, how will we know, or how is there a way to know when a system has reached equilibrium? And also, before we kind of move on, then this idea of saying, all right, well, if it's not at equilibrium, which way is it going to shift in order for it to reach equilibrium? If we don't have all reactants or all products, if we've got a mixture of reactants and products, how can we use this to predict what's going to happen next? And then, so this, in order to do this, we want to be comparing the concentrations at a given time to the equilibrium concentrations. But in order to work that out, we need to use our K value, our equilibrium constant, because we know that that is the ratio of the concentrations at equilibrium. So we can kind of work backwards from there to say, right, well, when is it, what is the concentration going to be at equilibrium? And how does that compare with where I am now? Okay, that's what we're going to look at. This idea is called the reaction quotient. So if we look at the reaction of A and B reacting together to form an AB, that then the reaction quotient is the ratio of the products to reactants regardless of whether the system is at equilibrium yet. Okay, so looking at the same sort of ratio of products over reactants, but at the concentrations at that time. So for K, we're talking about equilibrium concentrations. That's what these little EQ, BM kind of stands for, equilibrium. But then Q is saying, well, whatever the concentration is, we're going to look at the same ratio, products over reactants, based on whatever we're presented with. And then the idea is that whatever this value calculates to be allows us to make a prediction of what's going to happen. Is it at equilibrium? If not, which way is it going to go in order to reach equilibrium? But in order to actually be able to know that, we need to know the relationship between Q, this reaction quotient, and K, our equilibrium constant, because this is going to be the crucial thing that helps us to decide what's going to happen. The relative size of Q and K, is one bigger or smaller than the other, helps us predict which ways a system's going to shift in order to reach equilibrium. So if we look at saying, all right, well, at equilibrium, that Q and K are equal. Okay, because that means that the concentrations are at equilibrium. Whereas then, if we're not there yet, then Q might be bigger than K, or Q might be smaller than K, and then that will help us to work out what needs to happen. Okay, and so that's what we're going to unpack now. So we've got three situations that we might encounter: that Q is less than K, Q is bigger than K in some way, or that Q is exactly equal to K. And so what do each of these three things mean? Well, if Q is less than K, that means the equilibrium is going to proceed to the right. We have mostly reactants, or like we have more reactants than we should for at equilibrium. So we're going to favour the forward reaction to turn some of those reactants to form products. Okay, so if we think about it in terms of our fraction, remember that products is on the top and reactants is on the bottom. So if the Q value is too small, that means that the denominator, our reactant side of the ratio, is too big, and our product side is too small. And so then that's going to give us a smaller number than we will have at equilibrium. But then what happens if Q is larger than K? Well, then if we think about that fraction again, then it suggests that our product side is too large and our reactant side is too small. So the equilibrium is going to proceed to the left. So we're going to shift towards the left. We're going to favour the reverse reaction, turning products into reactants to form reactants. And what if Q is exactly equal to K? Well, that means that we are at equilibrium. There's not going to be any shift either way. We're not going to favour either reaction because we've reached that point where Q and K are equal, and so that we don't go any further from there. Okay, so if Q is less than K, then we're going to turn reactants into products. If Q is greater than K, then we're going to do the reverse reaction. If we've got it equal, then there's going to be no further change. Okay, so we make those calculations of Q and then we compare with K to help us to decide which is which. So we looked at when is a system at equilibrium. We looked at this idea that we want to know quantitatively whether the amounts that we have are at equilibrium or which way things are going to shift. We then looked at this idea that reaction quotient, or Q, can help us to determine this. When if we calculate it in the same process we would calculate K, our equilibrium constant, and then compare them, then it helps us to work that out. By comparing Q and K and working out which one is bigger or smaller, or if they're exactly the same, that helps us to know which way the shift is going to occur. Alright, thanks very much for watching. Don't forget to like and subscribe. Bye for now.